In this video, we'll talk about a very useful general idea in statistical learning settings, shrinkage or regularization. These ideas have widespread application, but we'll focus for now on their potential to help select variables to include in regression models. Previously, we outlined broad areas of methods to use to build models, and we talked about methods that select subsets of variables. In this video, we'll focus on shrinkage or regularization methods. To give a big picture overview, these methods mathematically penalize the inclusion of predictors that are only slightly informative of the response. The LASSO, ridge regression, and elastic net methods are commonly used shrinkage methods. Because all three share core conceptual features, we'll focus on the LASSO method for illustrating ideas. So, to motivate what is being done in the LASSO method, recall that the computational method used to find the beta coefficients in linear regression models was called least squares. In least squares, we find the values of coefficients that minimize a quantity called the sum of squared residuals, or RSS. A residual is the difference between the observed value of the response variable and the value predicted by the model. In minimizing the sum of squared residuals, the goal is to find coefficients that make our predictions as close as possible to the observed responses. A problem that can arise with the least squares approach is the potential for overfitting when the number of predictors increases. In the plot here, we have a data set with 20 observations, where all predictors were simulated to just be random numbers. We increase the number of predictors included in the model one by one, and we see that as the number of predictors increases, the sum of squared residuals is always decreasing. And in particular, when the number of coefficients is equal to the number of cases, we achieve the perfect RSS of 0. In general, this is a problem for the least squares approach. Including more predictors automatically improves the sum of squared residuals metric. In this example, the predictors were just random noise. And the fact that adding random noise predictors gives such clear improvements in RSS suggests that the least squares criterion is not ideal when there are lots of predictors being considered. It turns out that the LASSO method uses a modified criterion that helps in cases where there are lots of predictors. So, LASSO stands for least absolute shrinkage and selection operator, and the criterion that it uses to find good beta coefficients is to minimize a penalized version of the sum of squared residuals. The first part of this quantity is the familiar RSS, and the second term is an added penalty term. So, what exactly is being penalized, and how does this help us? If we look more closely at the penalty term, we see that it involves the sum of the absolute values of the estimated coefficients. In the LASSO method, we want to minimize this entire quantity, but this penalty term can only be positive. So its presence is hurting us in some sense. But we'll see that it also helps us in a substantial way by mathematically encouraging certain qualities in the estimated coefficients. To see this, we need to dig into the mathematical mechanics behind the penalty. We want this penalty term to be small so that this entire penalized sum of squared residuals is minimized. So let's ask, when is the penalty term large? In order to determine what features of the estimated coefficients are disincentivized. The penalty term can be large when a predictor has a large effect on the response, that is, when a coefficient is large in magnitude, a strong predictor. Although it may seem undesirable and potentially even counterproductive to have increases in the penalty with the inclusion of strong predictors, this ends up not being a big concern. More importantly, the penalty term is also increased if we have a lot of predictors with really tiny effects. It turns out that the LASSO method shines for this second reason. Let's dig a little deeper as to why. When lots of predictors have very small effects, we should be worried about overfitting. Why? Because our model is likely picking up on noise, random idiosyncratic variation that happens to look like a truly predictive feature just by chance. Lots of small effects amounts to saying we can decrease the sum of squared residuals just a bit more if we take a little of that predictor, a little of that other one, and just a little of that other one. This sounds a lot like overly reading into specific features of a single cat image when determining general characteristics of cat pictures. The fleck in the right ear, the orange tint of the nose, the discoloration of the fourth stripe all help me explain just a few more pixels of this cat picture. The penalty term gives us a penalty for having many predictors with tiny effects. The severity of the penalty is determined by lambda. The higher lambda is, the more severe the penalty, and severe penalties incentivize the coefficients for these weak predictors to be 0. Why? If those coefficients are 0, the sum of their absolute values is 0, and mathematically, no penalty is incurred. Another way to describe what the penalty term is doing is that it shrinks coefficients towards 0 so that less of a penalty is incurred. This is why LASSO is called a shrinkage method. A synonym for this in statistics and machine learning is called regularization. So, to reiterate, the LASSO method is a shrinkage method in that it incentivizes the coefficients to be closer to 0, shrinks their magnitudes towards 0. Also, because of the particular form of the penalty term being a sum of absolute values, LASSO is able to exactly set some coefficients to 0. This is a form of built-in variable selection. The variables that were selected to be in the model are the ones that did not have their coefficient set to 0 during the fitting process. Let's take a closer look at the tuning parameter lambda. We've said that the severity of the penalty is determined by lambda. So we can think of lambda as a fee to be paid for including a variable in the model. We only pay if a variable is included because lambda is multiplied by the estimated coefficient. If that coefficient is 0, the variable is not included, and we don't pay the lambda fee. Let's think about the most extreme values for lambda to get a better sense of how this penalty tuning parameter works. If we set lambda to 0, we're saying that we will impose no fee for having variables in the model. Any variables can be included without penalty. In this case, LASSO ends up being the same as ordinary least squares regression because the penalty term goes away. On the other hand, if lambda is infinite, then we pay an infinite fee each time a variable is included in the model. To minimize the penalized sum of squared residuals, then, we'd have to not include any variables in the model because even including one would incur an infinite penalty. This is shrinkage to the extreme because all coefficient estimates would be shrunken to 0. What we want is a lambda that is in between. Some intermediate fee that discourages us from adding a very weak predictor, one with a small coefficient magnitude, but also does not incur too much of a penalty for our strong predictors. Remember that because of that sum in the penalty term, all predictors get penalized. We want to choose lambda carefully so that the best model is chosen. Let's look at an example from the ISLR book on a LASSO model for predicting an individual's credit card balance. The response variable is credit card balance, and the dataset contains several predictors, including income, credit limit, credit rating, whether the individual is a student, and some other variables. The plot here shows how the estimated coefficients, plotted on the y-axis, change as the penalty lambda, shown on the x-axis, changes. As the penalty severity increases, the estimated coefficients move more and more towards 0. And eventually, most of the coefficients are set to 0 with a severe enough lambda penalty. A vertical slice of this plot corresponds to one particular model. In the slice highlighted here, all coefficients are 0 except the one for the credit rating variable. This indicates that the model chosen for this value of lambda has only rating as a predictor. How do we know which slice to choose? In other words, which lambda to pick? Well, for each lambda we can estimate the test error, the true error rate on new data, using cross-validation, and pick the lambda that gives us the lowest estimated test error. As a reminder, setting coefficients to 0 amounts to selecting a subset of variables to include, which is a way to combat overfitting. We can fight overfitting by not letting ourselves use weak predictors. So let's talk about a practical issue regarding the scaling of the variables that arises due to the penalty term. Given that the lambda tuning parameter penalizes variables based on the magnitude of their coefficients, it's important that all predictors be on the same scale. Otherwise, some variables will be unfairly penalized more than others. For example, let's say that the price of some fabric is well captured by the model, $4 plus $1 per centimeter. If we convert centimeters to meters, we have exactly the same information, but the coefficient for the length variable is multiplied by 100. In LASSO, the length variable will be penalized 100 times more in units of meters than centimeters. This isn't fair to the length variable. In practice, we standardize the predictors so that they all have mean 0 and standard deviation 1. This ensures that all variables are on the same scale and are penalized equally. We'll end the video with just a quick note on ridge regression, which was mentioned earlier as another shrinkage method. With LASSO, we modify the least squares criterion from linear regression by adding a penalty term that contains absolute values of the estimated coefficients. With ridge regression, we also use a penalized version of the sum of squared residuals, but this time we use the squared values of the coefficient estimates in the penalty term. Ridge regression and the LASSO share the same key concepts. Just like LASSO, ridge regression shrinks coefficient estimates towards 0 because of this penalty term. However, it does not automatically perform variable selection like LASSO does because coefficients are never set exactly to 0. We won't get into why this is the case here, but there's a nice graphical explanation in the ISLR book. So in summary, shrinkage methods try to select models in a very different way than subset selection methods like best subset and stepwise methods. Shrinkage methods use a penalized version of the least squares criterion that mathematically encourages weak predictors to be left out of the model. The lambda tuning parameter that is part of the penalty can be thought of as a fee incurred for variable inclusion. Choosing it well, usually via cross-validation, allows us to pick parsimonious models, ones that include only the most relevant predictors. Parsimonious models are also called sparse models, and we want sparse models because they are less prone to overfitting. Generally speaking, the ideas behind shrinkage and mathematical penalties are powerful ideas that are prevalent throughout statistical learning applications. As we move through the course, we'll see that these ideas come up for a lot of different methods as means of disincentivizing certain types of undesirable behaviors in our models.